Because this reaction is S only, we say that this reaction gives complete inversion of stereochemistry, R to S. Inversion to the other configuration. This reaction is also enantioselective because we only get one enantiomer. This product would be optically active. We've said before you can only get an optically active product if your starting material was optically active. Well, would this be optically active? Yes, it would. It's chiral, and it's only R, so this would be optically active, so it's okay to get something that's only optically active. This is our first ever enantioselective reaction. But we just started with one enantiomer. So that kind of makes sense. Okay, how do we get complete inversion? Before we look at that, the question, what's the mechanism here? And first question for that is an SN1 mechanism more or likely for this reaction compared to our previous model reaction? Is an SN1 more or less like SN1? The previous reactions on the previous page. Previous reaction, we said it was not SN1, right? The previous reaction, we said it was SN2. Why was it not SN1? What was the main reason? For the primary carbocation. If this reaction went SN1, what type of carbocation would we form? Secondary. So, is SN1 more likely or less likely? Less likely to form a secondary cation than primary? Talk about this reaction though. Is this one more likely or less likely than the previous reaction? More likely. Because this one would form a secondary cation, the previous one formed primary. Secondary more likely to form. Yeah? I agree? It is. It's more likely to be SN1 than the previous reaction. But is it SN1? Which mechanism is it? SN1 or SN2? Well, the stereochemistry tells you the answer. Because we get inversion. If the reaction had been SN1, what would the mechanism have been? What's the first step in the SN1 mechanism? From previous page and from your reviewing over the weekend, because these two mechanisms are hugely important to understand each step. What's the first step of SN1? Ionization. So let's do SN1. This ionizes, and this becomes boom, boom, boom. Secondary cation, we just said, which is more likely than primary, previous reaction. Okay? Then what's the next step? If this was SN1, we would then do what?
Attack.
Then hydroxide would attack. What do we call the second step? We gave it some terminology. How did we describe it last time? The second step was what?
Nucleophilic addition to carbocation.
Nucleophilic addition of the hydroxide to the carbocation would give that product. Hydroxide is now bonded here. But would it give only S? Will this only give S? How do you attack a carbocation? From the front or back? Front or back? Both. You attack carbocation from both. Okay? So if this was the mechanism, we should get what type of product? Racemic? We're not getting racemic. We're only getting S. It's not SN1. How do we get S? Because instead the mechanism here is SN2, and SN2 involves what? What's the SN2? How do you just, what does that involve? What do we we do in SN2 on the previous page?
The O.
Nucleophile attack, Nicholas?
Two bromine form a partial positive charge to secondary carbon, and then the hydroxide can attack and break it off.
Yeah, well, it's always a partial positive.
But if it did that, it would leave it in the SN amp. It would have to do backside attack.
This comes in here and kicks this off. Yes. And when you kick off a leaving group from a carbon, how do you do this? You said it.
That's backside.
Backside. Backside, right? Have we ever used backside attack? Have we ever talked about taking carbocation this way, that way? Guess what? I use this terminology when we do alkene reactions because it's coming. Here it is. Some books never use this terminology and all this is brand new, but you know all this already. You know backside attack already. You know how to attack carbocations. We're using that same stuff and we're just, okay? Because we learn fundamentals and then we use them. Okay? Not everything has to be brand new. We learn and we use and we apply. Backside attack. So the bromine is going back, so how does the hydroxide come in? Backside is actually front. It's backside compared to the leaving group. If the hydroxide comes in from the front, it's now bolded. And if it's bolded, well, that's now S if you can do a configuration. Backside attack gives inversion. Okay? Via backside attack. Nothing new. The stereochemical outcome here tells you the mechanism is SN2. The stereochemical outcome tells you the mechanism is not SN1 because SN1 would give racemic. Yes, SN1 is more likely here than the previous reaction, but it still ain't SN1. Okay, let's look at a closer look at how inversion is obtained. Backside attack is how it's obtained, but let's look at backside attack a little bit closer. Here's the same molecule, R. Same as that. Those are the same molecules, just drawn a little bit different. I've got the H drawn in. I've also got the bromine in the plane. Same molecule, same configuration, just different view. Hydroxide. The bromine, here's the carbon we're attacking. The bromine is that way. So the hydroxide is going to come in from where? Opposite side. We should call it opposite side, but we call it backside. Opposite the leaving group. That's backside. Opposite the leaving group would be over here. Hydroxide comes in over here. Hydroxide is negative. We're doing this same reaction. How many intermediates in going from there to there? No intermediate. Just a transition state. Let's look at the transition state. Transition state is where the bonds are partially making. This bond is starting to make here. I'm going to show the transition state separately. Mechanistically, we would do this. And we're going to kick this off. There's our mechanism. But there's a transition state in here before we get to the final product. Let's look see what it looks like. This bond is partially making, and this bond is partially breaking. Let's see if we can show that. Okay. Hydroxide partially making a bond to this carbon. I'm going to draw in the carbon. And then this bond is partially breaking. These three groups remain. But that is straight up. The H is still forward, but now it's straight down. And the methyl is still back. I really need to move this a little bit. These are eclipsed. H is straight down, and the methyl these two groups are supposed to be eclipsed, like this. The H is forward, the methyl is back. Okay? We get here. A lot of times these transition states are put in brackets. Maybe sometimes you'll see like a double dagger or something. Transition state, also called a activated complex. We'll look at this further. What's the charge of the hydroxide in the transition state? First off, where are we going? We'll get there. What's the charge of the hydroxide in the transition state? It's negative here. Negative here, it becomes neutral there. What is it in the transition state? Partial negative. The bromine is neutral. The bromine becomes minus in the product. What's the charge here as this is partially breaking? Partial minus. Okay, let's show the final product, I reckon. As the reaction completes, this becomes a full bond, and this totally breaks. So now we have hydroxide here, full bond to the carbon. Now these groups go this way. The H is still forward. Plus these electrons totally leave, and so that's how you get your fourth lone pair. And that's a minus. Do you guys understand how to do transition state? Somewhere between here and here, there's an energy level that's this bond is making, this bond is breaking. That's your highest energy, yeah? Transition state. The methyl and the H, like this. H forward, methyl back. When the hydroxide comes in, these things go like this. And now the H is right in front of the methyl. They're eclipsed. Then as this bond fully makes, these guys just move that way. H still in front of methyl. But they went from here to there as this came in. That's to make room. And this is called inversion. It's not like an umbrella that's facing this way and then it inverts in the wind and it goes the other way. Inversion taking place with this carbon. This is R. If you do this, it's now S. Importantly, though, this has sp2-like character. We can consider these sort of like p orbitals. And if we consider this sort of a p orbital here, where this is taking place, the remainder three groups are trigonal planar. Okay, these three groups trigonal planar. Because if these two are right in front of each other, and this one's straight up, you now have this trigonal planar. Okay, again, and that's just like an sp2 hybridized carbon. Trigonal planar with a p orbital. So it's sp2-like. sp2-like transition state. Now, since it's sp2-like, what type of bond angles do we expect between like the H and the methyl? They're like this, H4 methyl back, but what type of bond angle? Well, what type of bond angle do you have in sp2? (120), yes. (120-degree bond angles between your groups. What's the bond angles over here between the methyl and the H, or any of these bonds? 109.5. But in the transition state, these groups become 120. Or they need to become 120. Because they need to adopt this sp2-like transition state. Yes?
Why did the ethane switch that way? Does it not matter?
What do you mean switch?
Like it's facing that way to the left and this way.
What do you want? You want me to draw it like that
I mean, I don't know.
instead?
It makes more sense to me. I mean, I don't know.
It's irrelevant. This is a tetrahedral carbon. They're going to be distributed in a 109.5 arrangement. I mean, typically you draw these with 109.5 bond angles. And so the bond angle here, if I drew it like that, what is this bond angle? Well, it's like 45 degrees. Are you arguing that this is going to be a 45-degree bond angle? So I just drew it like this, which is more like a 109.5. But that doesn't change the configuration. The configuration is opposite of what we started with because it's been inverted. That is indeed S. That should be the same as that up there. But again, let's do it with the old hand here. Here are these groups here. My arm's the bromine. The remainder groups are all sort of that way. Here comes the nucleophile. When it comes in, these things go flat. Transition state. Okay? They were like that. They go flat. That's right behind them. But right now you have a penta, 5-coordinate carbon. 1, 2, 3, 4, 5. You know, like a 5-bonded carbon. That's transition state. Okay? But when this arm breaks off, instead of just leaving this empty space here, these groups move this way so that the carbon can then become tetrahedral again. So this hand starts out like this, flattens up. When this breaks off, these things come this way, and now my hand's broken. It's inverted. And now these things are pointed this way to move into the space where the bromine left. That's like an umbrella in the wind being turned the other way. It's called inversion. That's backside attack. Now a little touch of theory here. You remember when we drew orbitals, hybrid orbitals, and we said they had this back lobe that we never drew again? This is actually pumping electron density into that back lobe. Okay? That's it, 10 seconds. Not going to say anything else about back lobes. But theoretically, in advanced courses in math, you talk about that back lobe a little bit. That's why backside attack happens, because it's pushing into that back lobe to break that bond. Okay, important though, sp2 light transition state with 120-degree bond angles. This has to be achieved in the transition state. The easier this is achieved, the lower the energy of the transition state. If this is very difficult, transition state is going to be very high and the reaction is going to be difficult. Let's look at some applications of this, understanding the transition state. These two reactions here. This is where the I replaces the bromine by a substitution reaction. And we're focusing on SN2. SN2 transition state, right? Backside attack transition state. These two reactions, acetone to solvent, I replacing Br minus or Br. One reaction is faster than the other. Top reaction is faster. Why is that? Here's a relative rate. If this is called 1, this is much slower. Why is this reaction much slower? Right? What are we doing here? We got I minus. These electrons are going to come in here, backside, kick that off. Why is this slower? Here's your carbon. What type of bond angles do we need around this carbon in the transition state? (120-degree bond angles, right? We just said it. Okay. How easy is this going to achieve a 120-degree bond angle? Right now, from 8th grade geometry, that's 60 degrees, right? Pretty strained. How likely is this to become 120? Very difficult, right? You might even think, can it do it at all? Well, there's gray areas that we don't get into. But certainly, if absolute going to 120, very difficult to become 120. The question really is, which one of these carbons is more likely to be able to achieve 120-degree bond angles in the transition state? Top or bottom? Top, right? That's why it's much faster. It's able to achieve the transition state. Make sense? Questions about that example? Okay. Moving on. Let's look at reactivity of various electrophiles in the SN2 reaction. We're going to focus on SN2 a good bit. Next couple of pages. The electrophile is the species that contains the leaving group. Effective p orbital being immediately adjacent to the reaction site. These guys here are all very reactive in an SN2. Much more so than this guy. Now here the leaving group is chlorine, but I'm keeping it consistent. We'll talk about variations in the leaving group later. There's no variation here. Why are all these more reactive than this? Because all of these have a p orbital immediately adjacent to the reaction site. Here's the reaction site. We're talking about a nucleophile, yeah, coming in here and kicking that off. SN2, right? Adjacent to the reaction site, p orbital. P orbital. P orbital. 2 p orbitals there, but only one is needed to make it more reactive. Why does that make it more reactive? What does it affect? Do it? It makes what? Makes what more stable? You said it. What it would make? What would it be? What's the name of the structure that we need to focus on? If you're going to do a reaction, how do you make a reaction faster? Reaction coordinate diagram. If you're going to make a reaction faster here, how do you make it faster? We do this. Let's see, what if we raise this here? Well, let's not do that. Let's just stay here. Okay, boom. Which reaction is going to be faster, A or B? A or B, which will be faster? Okay, so why is reaction A faster? Lower activation energy. Okay, energy of what? You're looking at this energy right here? Or are you looking at the energy here? No, you're looking at it here. What is lower energy? Thank you. The transition state. That's the it. We want to make the transition state lower in energy. Do you know anything about the transition state of an SN2? Hopefully we described it up there. Why would a p orbital next door make this transition state lower in energy? That's what this implies, because if the reaction's faster, that means the transition state must be lower in energy. That's how it's going to be faster. Why would a p orbital next door? Well, when this reaction takes place, I erased it, right? You already got it drawn there. I'll try to redraw it real quick. We had this. We had carbon, right? Breaking. This was like a p orbital, right? And we had, what do we have here? This and this. What was for? H. Back methyl. Okay. Transition state has a p orbital, we said, like. Okay. What if we put a p orbital next door? Like on the adjacent carbon. What is this going to allow for? The p orbital that's formed in the transition state gets to interact with the p orbital next door. And is this a good thing or a bad thing? Good thing. It's almost like resonance in the transition state. P orbital next door overlaps with the p orbital transition state, lowering the transition state. P orbital next door is going to make it faster. Does this guy have a p orbital next door? When this transition state takes place here, you get like a p orbital here when these things are bonded, but is there one next door to stabilize that one? No. It's not going to be as reactive. P orbital next door makes these more reactive. These are actually also very toxic because they're very reactive. They'll react with your nucleophiles, your DNA, your proteins, which all have nitrogens and nucleophiles. Very reactive. This guy is much less reactive in SN2. Still can do SN2, we'll talk about it. Less reactive. Doesn't have the p orbital next door. That's propyl chloride. Ethyl chloride. Ever heard of ethyl chloride used in sports? Ethyl chloride, a lot of times they call it ethyl chloride because they don't know how to say ethyl. Ever heard of ethyl chloride? Baseball, the guy fouls a ball off his ankle, is like, the trainer comes out and sprays something on him. Ethyl chloride. What does this spray do? It makes the area real cold, numbs it, makes it cold so the pain is not there. How does this make it cold? because it's compressed liquid, and when it comes out, it immediately evaporates, and that takes heat away. And if you remove heat, you become cold, right? Right? You think that stuff is very toxic? No, they're not going to come out and spray toxic stuff all over the place. They have to evacuate the stadium. It's not that, okay, it's not that toxic. They would never come out and spray this on somebody. This would be bad news. It'll start reacting with your eye, proteins in your eyes, and you'll have tear gas, and you'll have all types of problems. Ethyl chloride, though, is okay. It's not as bad. All right? Why? Put your Orbital next door. Or not. It's very reactive towards nucleophile. Nucleophile substitution by called SN2. Okay, effective carbon substitution at nucleophilic site. Carbon substitution. Look at these guys. Leaving group is all the same, bromine. This guy is pretty darn reactive in SN2. It's more reactive than this, which is called a primary halide because the halide's on a primary carbon. Secondary halide, even less reactive. Tertiary halide, much, much less reactive towards SN2. Very reactive in SN2. This is not even primary. This is sort of just like parent. Okay? This is the slowest. In fact, this is so slow, never do SN2 with a tertiary halide. Too slow. It's so slow that the rate is near zero. Okay? Never do SN2. Secondary halide is okay. It's not the greatest. You can do SN2 there. In fact, at the very top, was that a secondary halide at the very top? Yes. Very top. That halide we did the SM2 on up there, that was secondary. Can do it, but it's not the easiest. Never do tertiary. Same thing in terms of toxicity. Methyl bromide, pretty darn toxic. Because the nucleophiles in your body come in here, boom, real fast and kick this off. What's the difference in these? Well, this is a carbon with a leaving group, right? And then it's got these 3 H's. How big are H's? Pretty small, right? Nucleophile, like on your DNA, okay? You got amino groups, which are good nucleophile. Bam! Kick that off. Transition state, SN2. All right. What if one of these groups becomes a carbon? What does it start doing here? It's like, okay, I can get through there. Well, what if more of them starts becoming carbons? Let's go ahead and make this tertiary. That is, it's bonded to 3 other carbons. And I'm making the H's a little bit bigger. But it's like, okay, here, hold on, I can get through. Here I come. Okay? It can't get back there because of all this congestion if you have other carbon groups. This is called sterics or steric congestion. All right? Sterics, steric effects, steric hindrance. Steric hindrance negatively affects the rate of an SN2 reaction. Okay? And the more substitution you have around the carbon that's leaving group on, the more sterics you have. All right? It can't get there, and it's like, forget about it. Okay? It's too crowded. I can't get through there. This guy has no sterics, very reactive. Tends to be toxic. Not quite as toxic. This is hard, it's very tough to react. It's probably going to require some heat to get this to react. This one, just forget about it. Ain't going to react. Too sterically hindered. There's the exact rates on the reaction over here. You can look at. That's again replacing one halogen with another. Lithium iodide, I replacing the bromine by an SN2 reaction. Acetone is just the solvent. And some relative rates given. Rates can be determined. Okay? And this is in line with what we just said. The tertiary halide, negligible or for us, 0 for us. Doesn't react. Let's take a trip to the dentist. Anybody ever been to the dentist? Ever received an anesthetic? Numb? Anesthetics can numb places, or they can be a general anesthetic and knock you out. But in terms of just numbing the area, there's different types of anesthetics, lidocaine. But the anesthetics have different lengths of duration. Some maybe last for 15 minutes, short acting. Other anesthetics may last for several hours. There would be longer acting. Okay. Well, in general, or typically, the rate depends on the sterics of congestion of the compound. I'm not showing a compound or anything, but the ones that last longer have more steric congestion around the reactive site. Because it's sterically hindered, hydrolysis of the compound is slower, and thus it lasts longer in the body. Okay? Because they last until the body degrades them, metabolizes them. The more sterically hindered ones, though, are going to be degraded slower and thus last longer. You can compare the structures of these. It's largely carbonyl chemistry, which is covered in Organic 2. The Lidocaine, I believe, is more sterically hindered around the carbonyl, more congestion, more substitution. Thus it lasts longer in the body. So it's an example of sterics influencing the rate of the reaction. So that's carbonyl chemistry, but it's still relevant. Okay, let's look at the leaving group. The leaving group of your halogens is iodine is greater than bromine. That means it reacts faster. Bromine reacts faster than chlorine. And then this is much faster than fluorine or fluoride. Okay? Typically, these are good leaving groups, with I being your best. Typically, we're not going to see F being a leaving group. It's just not good enough. This rate largely depends on the stability of the anion. Because when these leave, okay, they become anions. Well, which anion is most stable? I minus, because it's larger. Okay? So this makes sense. This is more willing to become an anion. It's more willing to leave. Right? When it leaves, it becomes anion, right? That's all the previous reactions, right? Right here. Right? Still there. When it left, it became Br minus. But I minus is most stable, so it's considered the best leaving group. And when we say best, it means it's going to react the fastest. Okay, halogens are good leaving group as they are, except for fluorine. What about other atoms, though? Can oxygen be a good leaving group? By the way, many of the things we're talking about, focusing on SN2, but they apply to SN1 as well. Okay? Oxygen is not a good leaving group on its own. For example, you take this alcohol and treat it with potassium methoxide. First off, you got to know structure here. All right? K is plus. That means all that is minus. Which atom is minus? Well, hopefully you know what M is a methyl, right? This is OCH3. So which atom is minus? Right? The oxygen's minus. That's just like KOH, right? Oxygen minus. Just it has a, instead of an H on it, it just has a methyl on it. It's the same thing though. Right? And this can act as a nucleophile and come in here and perhaps kick off this OH. Looks like an SN2. And that's how we would envision getting the O-methyl on here instead of the OH. The OH is now an anion and it can sit with the potassium. But guess what? This reaction ain't going to happen because the OH is not a good leaving group. If this was a bromine, then this would take place. Not a good leaving group. Hydroxide will not act as a leaving group in a slow rate determining step. On the other hand, we can get this to leave if we include acid, H+. Now this may or may not be a catalyst. It depends on if it's regenerated at the end. Sometimes it will be, sometimes it will not. H+. And this, we can activate the OH by first protonating it. And this gives, boom, boom, boom. We now have two H's bonded to the oxygen, one lone pair left, and that's a positive charge. So this is protonation of the oxygen, yeah? Strong acid. Typically strong acids supply H+, yeah? This will be a leaving group. A positively charged oxygen will leave. Now we can come in with something like methanol, and these electrons can attack here and kick off that, but it's not hydroxide that's leaving. What is leaving here? H2O, water. Okay? Water will leave if you supply a proton to allow it to be able to form. This will give what? Well, first it gives boom, boom. Now bonded to this carbon is what? That oxygen with a methyl and an H. It's a positive charge. Plus what? What did we form right here? When these electrons move on to the oxygen. That's water. An oxygen with two lone pairs and two H's plus water. That was your Lg. What do we need to do here, though, to get to a neutral product? We have to lose an H. Something had to supply an H. Maybe this was sulfuric acid and we have an HSO4 minus here. It goes with this. Now this can take the proton, and these electrons move here, and that would give what? That would give that product. Two lone pairs. But what do we reform here? H2SO4 reformed. So in this example, the H plus was a catalyst. It's reformed at the end. Now note in my reaction, we did not use H plus and methoxide. Note that you cannot do these two together, but these are not compatible. I've moved here. One attacked here and kicked off the water. What was the structure that attacked? Was it O minus or was it a neutral oxygen? Neutral oxygen. You cannot have a negative oxygen and an acid in the same reaction because a negative oxygen is a base, like hydroxide, right? You can't have hydroxide and acid in the same reaction. So the example that worked, we had to use the neutral nucleophile. Of course, often some things I say, you don't fully understand the context right now. It's in the notes. Maybe 2 days from now, that point will become a little more important. And I'll say, remember we pointed this out 2 days ago. Okay? So, everything is here. Comments are made. Okay, we'll continue ahead. Question before we end up.
So is this SN1 or SN2? Because
Well, what mechanism did we do, though?
we did SN1.
No, SN1 involves making a carbocation. The mechanism we just did we make a carbocation?
No, I thought SN1 meant, okay.
No, SN1 involves making carbocation. What we just did was we came in and we kicked off the water. But that was concerted. Nucleophile we had just kicked off the water. That's SN2. Keep asking. I think I know what you're looking at.
You know, it's
I think you're looking at number of steps. No.